Welcome to the deep dive. Today, we're getting really specific. We're looking at a piece of hardware that's pretty much invisible but absolutely critical in the industrial world.
It's the NTI E-RTDS-PAR540-6IN Pipe 100 ohm RTD sensor.
That's a mouthful. And our mission today is to figure out what all that means and, why a device like this is so important. Why it can be the difference between a smooth operation and, well, a disaster.
Right.
So let's just start with the basics. At its core, this thing just monitors the temperature on a pipe surface, right?
Exactly. It's the eyes of the system, keeping tabs on heat.
Right.
But the scope is what's really impressive.
Okay.
It operates from a really frigid minus 58 degrees Fahrenheit
Wow.
all the way up to a scorching 540 degrees Fahrenheit. So that's, minus 50 to 280 Celsius.
So it can handle both cooling systems and high-pressure steam lines, all with the same sensor.
That broad range is key.
And what about the physical design? I saw it has an adjustable ring.
Yeah, it's pretty smart. It's made to clamp onto standard pipes, anything from 2 inches up to 6 inches in diameter.
So is that a compromise? Or is it really optimized for that specific range?
Or definitely an optimization.
Yeah.
You need that consistent surface contact for an accurate reading.
Right.
And the ring design ensures that. But, the really critical part is the tech inside.
Right.
It's a 100 ohm PT 385 curve sensor. And that part of the name is, well, it's everything.
So what does that actually mean, PT385 curve?
PT is for platinum. And the 385 curve is an international standard. It basically tells any engineer anywhere in the world exactly how this sensor's resistance will change with temperature.
Ah, so it's like a universal language.
It is. It means you're not locked into one proprietary system. It guarantees interchangeability, which is a massive deal logistically.
Okay, that makes sense. But why platinum? Isn't that expensive? Why not use something cheaper?
2 words: precision and repeatability.
Yeah.
Platinum is incredibly linear and stable over time. And you can see that in the accuracy specs. Well, this is what's fascinating. At 32 degrees Fahrenheit, or 0 Celsius, the accuracy is super tight. It's plus or minus about half a degree Fahrenheit.
Okay, pretty precise.
But when that pipe heats up to, say, 212 degrees, the boiling point of water, that tolerance actually widens a little bit to about plus or minus 1.44 degrees.
So it gets less accurate as it gets hotter.
It's not a defect. It's just physics. And it's a critical piece of information for the engineer. It tells them they need to account for that shift when they set their alarm triggers. You have to understand the limits of your tools.
Right. So we've got this precise data. How do you get it from the sensor, which might be in a hot environment, back to a control room?
It comes with a 6-foot 3-wire lead. But, and this is a big but, you can't just plug it in, these devices almost never work alone.
What do you mean?
To work with NTI's bigger monitoring systems like the E5D or E16D, this sensor requires another little box, the E-RTDT-1562.
So it needs an adapter. Why the extra step?
It's more than an adapter. Think of it as a translator or a signal conditioner. The change in resistance the sensor is detecting is tiny. Minuscule.
Okay.
That module takes that tiny, noisy electrical signal and converts it into a clean, stable, and amplified signal that the main system can actually read and understand reliably. It completes the chain.
Got it. And I see it has RoHS approval. That's just a standard compliance thing, right?
Yeah, standard but important. Restricts hazardous substances. It's essential if you want to sell and deploy this thing globally.
So to sum it all up, this isn't just a thermometer. It's a highly specialized piece of equipment designed for repeatable, reliable accuracy on a very specific type of industrial pipe.
That's the takeaway, yeah. It's a benchmark for specialized measurement.
And it really shows you that something as simple as measuring temperature requires this incredible level of calibrated platinum-based precision.
Absolutely, because the stakes are just so high.
Which brings us to a final thought. I want you to consider a massive system that relies on this. Think about a data center's cooling system or a manufacturing line. What happens if a sensor like this monitoring a critical line is off by just 1 single degree? Not enough to trigger a major alarm, but it's just wrong consistently. What are the ripple effects of that tiny error over weeks or months? The wasted energy, the slow degradation of multi-million-dollar equipment, all because of 1 degree. That's really the hidden cost of imprecision.